algorithm requires global knowledge of the network topology and the link costs to be available at every node. In contrast, the Bellman-Ford algorithm has a different approach. Nodes only communicate with immediate neighbors, and they can iteratively update their routing tables through this interaction. So it is distributed and asynchronous, and it does not require global knowledge of the topology, simply the cost to each neighbor. The problem that you can imagine comes together with this is if a node's neighbor has incorrect information, the node will use incorrect information in turn in revising its own routing table, and this can result in poor response to link failures. For example, there are sometimes non-recoverable failures, such as the count to infinity problem. To see this problem, you can take a look at exercise 7.7 in the textbook. So let's study the Bellman-Ford algorithm. The idea essentially rests on the Bellman equation, or maybe the Bellman-Ford equation. So WUI star is the currently best known cost from node U to node I. And this is updated as the minimum out of all nodes J that are neighbors of node U. Neighbor of node U means there's a link between node U and node J. Okay. The cost, the direct cost from node U to node J plus the cost of node J, the best available cost of node J to node I. Okay, the principle why this is optimal is that if the minimum cost path from U to I passes through some node J, then the part of the path from J to I, this path from J to I, must be a minimum cost path from J to I. Why? Well, because assume the contrary. Okay, suppose there was actually another lower cost path from node J to node I, okay, which has this path PJI tilde, which for the sake of contradiction we assume has lower cost than the path PJI star. Okay, well, in that case we could concatenate the path PJI tilde to the path from node U to node J and improve the overall cost from node U to node I, which is a contradiction. So that proves the principle. Okay, so here is the algorithm that basically rests on that principle. For every node in the network, let's say U, do the following. First of all, we initialize. For every node other than U, we initialize the cost to that node to the immediate link cost if that node I is a neighbor of U, and otherwise set the cost to infinity. Okay, and let NUI be I if I is a neighbor. If I is a neighbor, then clearly I would be the next top node to I. Okay, otherwise we don't know the next top node yet, so initialize it as -1. So this initialization step is similar to the Dijkstra algorithm, but notice that in Dijkstra's algorithm we were setting previous hop nodes, and here we're setting next hop nodes. Okay, now here's the main iterative step. For each node U sends out its current costs to all of its neighbors. Of course, only if this cost was updated during the previous iteration. Okay, so this is one iterative step, and at the moment we don't know how many iterative steps there will be, but we'll prove later on that the algorithm will converge. You know, if all the costs are static, of course, the algorithm will converge in at most n steps. Okay. Now, for every node, okay, now that every node has received updated weights from each of its neighbors, the node checks whether it can reset the costs to some better costs, meaning for every node I for which the current cost to I is not the minimum achievable currently by going to a neighbor and then going from that neighbor to I. Okay, then we reset the cost to that node I, because we found out that by going first to some neighbor J, and then going from there to node I, we can get a better cost than however we previously went to node I. Okay, then the next top neighbor would then be set to that particular node J, that particular neighbor J, which has the best path to node I. Okay, so we do this for every node in the network, and then every node in the network does it for every other node in the network. And then, as you can see, once nothing changes in an iteration, the iterations will stop. Okay, here's an example. Initially, so here let's focus on node C. Okay, every node is trying to get to node C. So basically, this is the routing table entry for every node that points to node C. Okay, so initially WAC, WBC, WCC, WAC, WBC, WDC, EC, and FC are all set to infinity because these nodes do not have, initially none of the nodes have a routing have a finite routing table entry, have a finite cost to node C. And then we reset the cost of the neighbors B and F to 2 and 2. Okay, and then after one iteration, since B and F will broadcast to all of their neighbors these costs, node A will be able to update its distance to C as CAB plus WBC, which will be 3 plus 2, 5. And then the node D, for example, will be able to update its distance to 1 plus 2, which is 3. Okay, you can see that if we do one more iteration where all the nodes broadcast their distances, these entries will not change, hence the algorithm will stop. Okay, now the algorithm terminates after at most n-1 iterations. Why is that? So let's state it formally. Assume that a minimum cost path from node U to node I consists of k hops. So suppose that a minimum cost path from node U to node I consists of k hops. It is quite easy to prove that node U obtains the true minimum cost and the next hop after the kth iteration. So once the kth iteration is done, the cost of node U has been set to its optimal cost, and it's not going to change after this. Once we prove this, a consequence of that, if the network has n nodes, clearly there cannot be a path longer than n-1 links. Therefore, the Bellman-Ford algorithm must terminate after at most n-1 iterations. So let's prove the first statement. Note that in a network with, so basically, we'll use induction. The statement clearly holds for k equals 1. Okay, if the optimal path to a certain node has length 1, okay, then that will be obtained in the first iteration, and it's not going to change after that because it's assumed to be optimal. Okay, and it will be obtained after the first iteration because in the first iteration, remember, we're going to all the neighbors. Okay, and we reset their costs to their direct link costs. Now we'll use induction. Suppose the first sentence holds for iteration k-1, that is, at the end of iteration k-1, node U has obtained the shortest path to any node for which the minimum cost path has length k-1. Okay, now take a node I for which the minimum cost route has k hops. We'll show that this path will be found at the kth iteration. Why is that? Because consider the next node on the minimum cost path to I. Note that J has to be a neighbor of U, so that in the kth iteration U will compute Cuj plus Wji, as Wji is a minimum cost path of length k-1, this computation will determine a minimum cost k node path. That is, at the kth iteration, the node U will compute Cuj star plus Wj star I star, and the minimum out of all nodes j, which are not j star, that are neighbors of u, cuj plus wji. And out of these, it will select the best. Okay? Now, since we assumed that node I has an optimal path that is at distance exactly k plus 1, the result of this comparison operation will give us this optimal cost, which is which will be the k node path. Okay, so because of this, since at every iteration the final routes for nodes that are k hops away in the optimal route are found, and in a network with n nodes, the longest loop-free path has at most n minus 1 hops, the algorithm terminates after at most n minus 1 iterations. Okay, so that brings us to this end of the description of the Bellman-Ford algorithm. In the next